Thank you, and thanks to the organisers. It's nice to be here for a while. I now talked about connections between group theory and the rest of mathematics. He was particularly interested in what the rest of mathematics can do for group theory. I will, particularly in my talk tomorrow, be going in the other direction, how you can use what we know now about groups to get results about semigroups and automata and various things like that. But the applications will be via permutation groups. So I'm going to take the word introduction in the title of the workshop seriously and try and give you a general introduction to permutation group theory as it is now, with a few little detours along the way, a few little interesting sidelines as we go. So, that one. Okay, right. So, groups are given to us to act on something, and this has always historically been the case. So, originally, groups meant symmetry groups of things. Then they became permutation groups, groups of permutations of a set. So a set of permutations closed under composition and inversion containing the identity. And then finally we got to the modern abstract definition of a group as something satisfying the group axioms. And at each stage in this development it was necessary to verify that the concept, I mean, the things that we were calling groups hadn't changed, even though the definition had. In other words, that a symmetry group is a group of permutations on the object that it's symmetries of, but that every permutation group is a symmetry group, and that a permutation group satisfies the group axioms, but anything satisfying the group axioms can be represented as a permutation group, namely Cayley's theorem. So you can look at it from various points of view. I'm going to take the permutation group point of view. So a permutation group will just be a subgroup of the symmetric group on a set omega. And of course, closely related to that is an action of a group, which is a homomorphism from G into the symmetric group on omega. So a homomorphism whose image is a permutation group. And the message is that if we understand the abstract structure of a group, we can describe its actions, and in the other direction, if we know enough about the actions of the group, we can say something about the abstract structure of the group. So, right, permutation groups, that's what I'll be considering. And a bit of notation. The number of points in the set omega is the degree of the permutation group. I will usually assume that this is finite in this talk, but there are very interesting things about infinite permutation groups, which you won't hear any of from me today, unfortunately. We're interested in various properties of permutation groups, and I want to take, as far as possible, a uniform way to define permutation group properties. You see, in any kind of mathematics, we want to describe an arbitrary structure by somehow splitting it up into smaller ones, describing the smaller ones, and then understanding how they get put together to get the larger ones. So I want to define the sort of properties we'll be using in a uniform way. So we have our set omega that we're acting on. If you have any kind of structure on omega, I will say that the structure is trivial if it's preserved by all the permutations in the symmetric group, and of course it's non-trivial otherwise. So, for example, what are the trivial subsets of omega? Well, only the empty set and the whole of omega. Any other subset will fail to be invariant under some permutation. What are the trivial graphs on omega? The null graph, the graph with no edges, or the complete graph with all possible edges, because if you had a pair joined by an edge and another pair not joined by an edge, there would be a permutation in the symmetric group that would carry one to the other, and that wouldn't preserve your graph. So that's what I will mean by trivial structures, and you'll see several other examples as the talk goes on. But so what does it mean for a group to be transitive? It means it preserves no non-trivial subset of omega, right? So the usual definition is that if you have any 2 points of omega, you can map one to the other by some permutation. Why is it the same? Well, suppose that there are no non-trivial subsets preserved by G, and let's take 2 points alpha and beta. If you couldn't get from alpha to beta by any element of the group, then there would be a subset of omega consisting of things that you could reach from alpha, and the group axioms, the closure axiom, would then imply that you can't get out of that set, so it would be a non-trivial G-invariant subset. So that's the sort of way in which you can take standard permutation group definitions and put them into this framework of preserving no non-trivial structure of some sort. So just first little digression. So derangement is a permutation with no fixed points. If G is a transitive permutation group of degree greater than 1, then G contains a derangement, and indeed it contains a derangement of prime power order. So the first part is due to Jordan, and it's elementary. The orbit counting lemma, or what some people call Burnside's lemma, but if Jordan was using it, it clearly wasn't Burnside's lemma, says that the average number of fixed points is equal to the number of orbits. So for a transitive group, that's 1. And so if the average number of fixed points is 1, the identity fixes more than 1 point, so there must be an element that fixes less than 1 point. And that's got to be a derangement. So absolutely straightforward. But I do recommend you, I'll give you the reference at the end. There's a beautiful paper by Jean-Pierre Serre called On a Theorem of Jordan. He takes this theorem and a more recent improvement of it and recasts it in the language of several different areas of mathematics, uses it to prove non-trivial things about topological spaces, modular forms, all kinds of things. A wonderful paper, well worth having a look if you don't know it. What about the second part? So we've just added this little phrase of prime power order. How do you prove that? This is due to Fine, Cantor, and Schacker. And as I heard the story, Fine and Schacker are number theorists. They were looking at relative Brauer groups of global field extensions. They needed a certain group theoretic result, namely this one. And so Cantor was the hired gun who did the job for them. Murray Schacker told this to Lewis Nowitz, who passed it on to me, in exactly those words. Anyway, so how do you do it? Well, you have a transitive permutation group. I mentioned that we do various reductions. You reduce it to the case where the group acts primitively and the group is simple. Now, we have the classification of finite simple groups. If it's a simple group, it must be an alternating group, a group of Lie type, or one of the sporadic groups. In each of those cases, we have a transitive action of that group, and we want to find a derangement of prime power order. So in other words, for every maximal subgroup, we want to find a conjugacy class of elements of prime power order outside that subgroup. So it's case by case through all these finite simple groups. Now you compare that to the simple argument for Jordan's theorem. So I think this is an interesting challenge that I would like to see the answer to. Is there a more elementary proof of the Fine-Cantor-Schacker theorem? There is actually more to it. The application was, as I said, to relative Brauer groups of global field extensions, and the statement is that these are infinite. If you could prove that directly, you could reverse engineer this and get this theorem about derangements of prime power order. So a direct proof of that number theoretic fact would give this group theoretic fact here. So that might be a way to go if you were interested in doing that. Anyway, so that's by the way. So let's go back to the main thing. How do you build up arbitrary groups from transitive ones? Well, you look at the minimum non-empty G-invariant subsets. These are the orbits. And if 2 points belong to the same orbit, there's an element of G mapping one to the other by essentially exactly the argument I used there. And so G has a transitive action on each orbit. So you take a number of transitive actions of the group, just stick them together. But if you're interested in what the actual group is, it's a little bit more complicated because the group G is not uniquely determined by the transitive constituents. If you had a group with two orbits of size 2, then on each orbit you see the cyclic group of order 2, but you don't know until I tell you whether the whole group is C2 acting simultaneously on both orbits or whether it's C2 cross C2. So there is a little bit of work needed to be done there. G is a subdirect product of the transitive constituents, but there may be several subdirect products and you don't know a priori which one it is. But in any case, for many purposes, it is enough to study transitive groups. So you can take a transitive action of a group and write it entirely within the group. So if H is a subgroup of a group G, then G acts on the set of right cosets. Martin called these G colon H in brackets, I think. Is that right? So anyway, it's just the set of right cosets. G acts by right multiplication, and this action is transitive. And conversely, every transitive action is isomorphic to an action of that form where you take H to be the stabilizer of a point in omega. So every transitive action can be internalized to something within the group, the action on the coset space. So in more detail, the subgroup H will be the stabilizer of a point of omega, and if you look at all the elements of the group mapping alpha to beta, that will be a right coset of the stabilizer of alpha. So like that. So we don't have to deal with arbitrary actions. We can just look at subgroups of the group and for each subgroup build a coset action. Indeed, we can even cut it down further because two of these actions are isomorphic if and only if the subgroups are conjugates. So we only need to look at the conjugacy classes of subgroups. Right, primitivity. So now we look at partitions of omega. What are the trivial partitions? There are two of them if omega is bigger than 1. There's the partition with a single part, and there's a partition into parts of size 1. Those are the only SN invariant partitions. So we say a group is primitive if it preserves no non-trivial partition of omega. So when I was a student, my first job was to read Wieland's book on finite permutation groups. The description is a little bit more complicated in there. This is the simplest way to say what it means for a group to be primitive. But we've put in transitive there, so we've included the fact that there are no G-invariant subsets. Why? Because if you take a set of 2 points, it has only 2 partitions, the trivial ones. So every partition is trivial, so every subgroup of S2 fixes no non-trivial partitions, and that includes the trivial group. And there's an interesting spin-off of this. There's been some reference to diagonal groups, and I will say quite a lot more about diagonal groups later on, but diagonal groups with 2 factors can be primitive without having anything interchanging the 2 factors. That's not possible for larger number of factors, and that's because in a diagonal group, for it to be primitive, the group permuting the factors has to have no G-invariant partition, but doesn't have to be transitive. But anyway, we prefer primitive groups to be transitive, so we actually have to put that in to exclude that one single case. Right, so any transitive action is isomorphic to the action on a right coset space, and many of you probably know this already. The action is primitive if and only if that subgroup is a maximal proper subgroup of the group. So for primitive actions, we're looking at coset spaces of maximal subgroups of the group. And there's another thing you can say here. If you have a normal subgroup of G, then the orbits of n form a G invariant partition. That follows directly from the definition of normal subgroup. So if the group is primitive, either n is transitive or the action of n on omega is trivial. So that means that normal subgroups of non-trivial normal subgroups of primitive permutation groups must be transitive. And so particularly Cheryl Prager has taken this idea, and which actually goes back to Galois. Peter Neumann, who's probably read Galois' works more carefully than anyone else, points out that Galois himself was a little bit confused between primitivity and quasi-primitivity, and sometimes he uses one concept and sometimes the other. But so quasi-primitivity, what is this? Permutation group is quasi-primitive if every normal subgroup is either transitive or trivial. So any primitive group is quasi-primitive, as we've seen. But for example, as I think someone also mentioned, if G is a simple group, then any transitive action of it is quasi-primitive, because the only normal subgroups are the identity, which acts trivially, and the whole group, which by definition acts transitively. So the class of quasi-primitive groups is larger than the class of primitive groups. So Anna told us something about this, which I'll come to later. But I don't know how to define quasi-primitive in this general scheme of definition that I've had before. Is there some kind of a structure so that a group is quasi-primitive if and only if it preserves no non-trivial structure of that type? I don't know how to do that, and I don't think there's an easy answer to it, but it might be that by delving a bit deeper into the finite simple groups, we could find an answer to that question. I think it would only be a curiosity if we did. This is not one of the big problems that needs to be solved, but I think it's an interesting curiosity. Is there a definition of quasi-primitive along those lines? And as I said, Cheryl Prager and her colleagues have been done some of the major work on quasi-primitive groups. So let me just go back to imprimitive groups for a minute. If G preserves a non-trivial partition, can we build it up in any sense? Yes. So we have a partition of omega. Preserved by G. That means that each part of the partition is mapped to another possibly equal, possibly different part. The parts can't be smeared out over the whole thing. And that means that you see already one group. You see a group of permutations of the set of parts of the partition. And there's another group that you can see. If you stabilize one of the parts and just look at the permutations that act within that part, that gives you another smaller permutation group. And so can we reconstruct the whole group from that? Well, we're in the same situation as we were for intransitive groups. We've got these two, and so we get an embedding of G into, not this time the direct product, but the wreath product of those two groups, H being the group acting within a block, K the group permuting the set of blocks. So an imprimitive group is, if I can coin a phrase, a sub-wreath product of these two smaller groups, in the same sense that an intransitive group is a sub-direct product. And so, in a sense, this says if we understand enough about primitive groups, we can get knowledge about arbitrary transitive groups. So I want to say a bit about a particular type of primitive groups, those that preserve Cartesian structures. So a Cartesian structure on omega is an identification of omega with the set of n tuples over a subsidiary set X. So non-trivial if n is greater than 1. And there are various ways you can think of a Cartesian structure, and some of you might know the book by Cheryl Prager and Chava Schneider that came out last year, Permutation Groups in Cartesian Structures, which is all about how to recognize these things, how to pull information out of them, and so forth. But one way of thinking of it is, if you're a coding theorist, x to the n is a set of words that you might want to transmit, and the distance between two words, the Hamming metric, is the number of coordinates in which the two words differ, or in coding theory terms, the number of errors that you would have to make to change one word into the other. So you can think of a Cartesian structure as the set of n tuples with the Hamming metric. That would be another way of regarding it. So again, if G preserves a Cartesian structure, we can get two smaller permutation groups, H and K. H is the group, so this time we're not acting on a partition like this, we're acting on the set of words of length n. So you can look in a particular position and you can say, how are the letters occurring in that position permuted by the group? And you can also say, how are the coordinate positions being permuted by the group? And once again, you find that G is embedded in a wreath product of those two groups, but with a different action. This is what's sometimes called the product action of the wreath product, rather than the action that we had before for imprimitive groups. So if G preserves a Cartesian structure, it is embedded in a wreath product of smaller groups. And as I say, the book by Prager and Schneider will tell you what you need to know about those things. So I'm going to make a further reduction. I'm going to say a permutation group is basic if it is primitive and preserves no non-trivial Cartesian structure. So this is exactly the same format of definition as we've had before. So these are the basic groups. They're primitive and they preserve no Cartesian structure. So this is the Nan Scott Theorem, which has been referred to before, and we've had quite a bit about it. So I'll say a little bit about the history. So in 1979, there was a conference in Santa Cruz. At that time, everybody thought that the classification of finite simple groups was imminent. Gorenstein was just about to announce that the classification had been completed, somewhat prematurely, as it turned out, as we know now. But I didn't go to that conference, but I had a sabbatical in Sydney immediately afterwards. Terry Gagan had been at the conference and had a copy of the preliminary conference proceedings, and it contained a paper by Michael O'Nan and a paper by Leonard Scott, both stating the theorem. So the Nan Scott Theorem was stated by both of those authors, and for some reason which I do not know, O'Nan's paper did not appear in the final printed version of the proceedings, whereas Scott's did. And that's why we refer to Scott's paper there. But O'Nan and Scott both had papers proving exactly the same theorem in the preliminary version of the proceedings. But later on, Peter Neumann pointed out to me that if you read carefully Jourdain's Traité des substitutions, most of Nan Scott is in there. And it was forgotten for 100 years. Why was it forgotten? I suspect the answer is the Nan Scott theorem really becomes useful once you know the finite simple groups. If you don't know the finite simple groups, it's a nice theorem, but you can't actually make much use of it. And so it wasn't until the classification of finite simple groups was imminent that it was worthwhile to start looking at primitive permutation groups in this way. So anyway, that's just my theory. I have no evidence for it. But for example, I'll come later to a theorem of Burnside, which is a very special case of what Jourdain did. Burnside thought it worth stating it independently, so he maybe didn't know what was in Jourdain's traité. Anyway, here's the Nan Scott Theorem. Here's my version. Now, this is not an elaborate, complicated version. This is pared down to the simplest possible form. This is the Nan Scott Theorem. A basic permutation group on a finite set omega is affine, diagonal, or almost simple. So we have only 3 classes now. We've pushed the Cartesian or the Reith product ones under the rug by using this word basic, and we have just 3 types. So I'm going to say a little bit about the 3 types in the theorem. So affine groups, well, the full affine group is the group you take a vector space and you take all maps of the form invertible linear transformation, add on a constant vector, right? So the constant vectors form a normal subgroup, the translation group, there it is, T, and the whole group is a semi-direct product of T by the general linear group. So an affine group will mean a semi-direct product of T with a subgroup H of the general linear group. So you must include the full translation group, but you're allowed to take any group of linear transformations. You don't have to take the full group. So that's affine. And you can show G is primitive if and only if H is irreducible on V. That's essentially because T is acting regularly, and the invariant partitions for a regular group are precisely the coset partitions, and so basically that tells you, because we're over the field of, we can work over the field of P elements, so the cosets of subgroups are the cosets of subspaces, and if there's no invariant subspace, there's no invariant coset partition. So G is primitive if and only if H is irreducible. G is basic if and only if H is primitive as a linear group, that is, preserves no non-trivial direct sum decomposition of V. Right? So we can recognize primitive and basic. We've sort of shifted the problem now from permutation groups to linear groups. So we've turned it from permutation group theory to representation theory. And so for further studies of affine groups, if it's base, so C1 are the non-irreducible, C2 are the non-primitive, so we've got rid of those 2, so we have classes C3 to C8 and S, and Kolb has explained to us how this theorem of Aschbacher works, so we know essentially how to attack groups of affine type. Diagonal groups. So I'm not going to give you a precise description of diagonal groups, but I will say more about them. And this may be a way that is not entirely familiar to you. Basically, okay, so here is a description that will do for now. You take a non-abelian finite simple group, a natural number greater than 1, you take the dth power of T, let it act on the cosets of the diagonal subgroup, and in the case D equals 2, there's a simpler description which may be familiar to some people. You've got 2 copies of T, but now we're acting on the cosets of the diagonal group, and you can transfer this just to an action on the group T itself, because either direct factor is a complement for the diagonal group, and so we can index the cosets by one of the direct factors, and then the first factor acts on the left, second factor acts on the right, and we have to put an inverse there to get an action. And the normalizer of T to D in the symmetric group also contains what? Well, automorphisms of T acting component-wise, and the symmetric group SD permuting the components. So those things all together generate the full diagonal group, and a diagonal group, a primitive group of diagonal type, will be a subgroup of the full diagonal group containing the SOCL, which is this T to the D. And in the case D was 3, and I will come back to this tomorrow in my lecture, the full diagonal group is the automorphism group of a certain graph associated with the Cayley table of G. So you take the Cayley table of T, that's a Latin square. From any Latin square you can build a strongly regular graph. The vertices are the cells of the Latin square. You join two vertices if they lie in the same row or in the same column or if they have the same entry. That gives you a graph. The automorphism of that, if the Latin square is the Cayley table of a group, let's say a finite simple group, then its automorphism group is the 3-factor diagonal group. Okay, and almost simple are just almost simple. They lie between a simple group and its automorphism group. And the classification of finite simple groups tells us that the Schreier conjecture is true, so basically tells us that the quotient automorphism group of T over T is very small, and so the possibilities for G are extremely limited given T. So these are the almost simple groups, it's worth pointing out this is the dustbin case into which everything is thrown that you can't understand. The point is that in the non-basic case, the Cartesian structure case, in the affine case, and in the diagonal case, I've told you exactly what the action of the group is. Here I haven't told you what the action of the group is, because we don't know. It's just an almost simple group acting in some primitive action. Right, so when the classification was proved, a number of problems that had been absolutely untouchable before suddenly all fell, including the classification of the multiply transitive groups. So a group is 2 transitive if it preserves no non-trivial directed graph on omega. Another way of saying that is that you can map any ordered pair to any ordered pair of distinct points to any other ordered pair of distinct points by some element of the group. And more generally, T-transitive if you can map any T-tuple of distinct points to any other. And you can phrase that in terms of some sort of oriented hypergraphs if you wish to do. So the symmetric group is n-transitive. The alternating group is n-2 transitive. You can put n-2 points anywhere you like, but you can't swap the last 2 around because that would be a transposition. Mathieu discovered 2 more 5-transitive groups and 2 more 4-transitive groups. These are the Mathieu groups. It's not clear how he found them, and he basically just said these permutations generate a group with these properties, and in the days before Magma and Gap it would have been quite an effort for one of his contemporaries to verify his assertions. I don't know how the paper was refereed, but so one thing that Mathieu knew is that primitive groups other than Sn and An, there are none for n less than or equal to 4, that's too small, but for every n from 5 to 33, he was able to construct a primitive group other than Sn or An. But M22 and its automorphism group are the only ones at degree 22, so he couldn't have done that without constructing his sporadic simple groups. And there's no direct evidence for this, but there's some thought that he believed that this was the general pattern, that almost every n or perhaps almost every n would be the degree of some primitive group other than Sn or An. Well, you know that's not true because Anne told us that earlier on, but let's just say a little bit about multiply transitive groups. The question of which ones exist was really one of the defining problems of permutation group theory for well over a century. So are there any 6 transitive groups other than symmetric or alternating? Wieland found a bound of about log n and also showed that modulo the Schreier conjecture there are no 8 transitive groups. Nagao improved this to 7 and Onan to 6. But Burnside knew that a two-transitive group must be affine or almost simple. Now that's a special case of Nan Scott, but Burnside wrote down a proof. It's easier in the two-transitive case, but he actually took the trouble to prove it because probably he didn't know Jourdain. And now we have a complete list of the two-transitive groups. And from the list, you can just look at it and verify that there are no six-transitive groups apart from symmetric and alternating groups. And many people contributed to this list. I think the only one here is Martin, but anyway. So this is a footnote to Mathieu, as Anna told us. So I'll go quickly through this. Before I do, there's no primitive group of degree 34 other than Sn or An. But prior to the classification, that would have been a really tough job to prove. It probably could have been done, but probably would have been worth a PhD. Now, you just ask Magna or Gap for how many primitive groups of degree 34, and they will tell you 2. So Peter Neumann, Dave Teague, and I showed this result that Anna mentioned. The number of integers less than x for which a primitive group other than Sn or An exists is asymptotically twice the number of primes less than or equal to x plus some constant times the square root of x plus order of root x over log x. Now, there's something to be said about this. You can push this series, this asymptotic series, further if you want to, but if, for a number theorist, you would not bother to push it further. Why? Because the difference between pi of x and x over log x, which is its standard analytic approximation, is bigger than the next term in the series, even if the Riemann hypothesis is true. The truth of the Riemann hypothesis would say that the difference between pi x and x over log x is as small as it could possibly be, which is x to the half times a little bit. But you see the next term in the expansion is, and these terms all come from particular families of groups. And I showed you these ones. They're the cyclic group of order p and PSL2p of degree p plus 1. Here you have Sm reth S2 of degree m squared and Sm acting on two-element subsets of degree m choose 2. And then you get down to this. Here you have groups whose degree is quadratic in a prime, such as PSL2p squared, PSL3p. And you can go on. So this has been extended to quasi-primitive groups, and Anna told us about this, and you have to replace the 2 by a different constant. But the other thing that we can do now, of course, is you can ask Magna or Gap for the primitive groups. Up to 4,095, it has the complete list, which I think is probably now correct. There was a mistake in it until fairly recently. But anyway, you know, if we couldn't even have done 34 before the classification, what chance of doing 4,095? Anyway, so there it is. So here's another little story, set transitivity. Very famous book on game theory of games and economic behavior by von Neumann and Morgenstern. In this book, they have a chapter on n-player games. Now, n-player games are much more complicated than the two-player games whose theory we teach to undergraduates, because with n-player games you can have coalitions, and the structure of coalitions is very important in how the game plays out. And so they defined what they called a fair n-player game, which meant that no set of players can have any structural advantage over any other set of the same size. So it's a way of saying that everybody is in the same boat when it comes to making coalitions. So to do that, they said, which are the permutation groups that are transitive on the sets of size t for every t between 0 and n? So they posed this question. In the second edition of the book, they said, this question has been solved by Chevalet. I don't think Chevalet ever published that, Beaumont and Peterson published it, but made no reference to von Neumann and Morgenstern. But apart from the symmetric and alternating groups, there are just 4 such groups, 4 little groups with those degrees. Remember that kind of theorem, because this will come up in my talk tomorrow. And so, more generally, permutation group is 2-set transitive if it preserves no non-trivial graph on omega, which means it's transitive on the set of 2-element subsets of omega. And T-set transitive is the obvious generalization of that, sometimes called T-homogeneous, but I'm a little wary of that term because in infinite permutation groups the word homogeneous has a completely different meaning, and it's easy to get confused. Anyway, so let's just have a look at this set transitivity condition. T homogeneity is equivalent to n minus t homogeneity, because if you can map any t set to any other t set, the complementary n minus t set will go to the complementary n minus t set. So those are equivalent, and therefore we might as well, if we're interested in these groups, we might as well assume t is less than or equal to n over 2. And it's a lovely paper by Livingston and Wagner in 1964, where they show that, first of all, T homogeneity implies T minus 1 homogeneity using representation theory, but in fact you can translate their argument into elementary combinatorics. The advantage for doing that is that then it works for infinite groups as well, whereas the representation theory argument doesn't. And they further showed that for T at least 5, such groups are T transitive. So the difference between being transitive on unordered sets of size T and ordered T tuples, they're equivalent for T at least 5. Then if T is 2 homogeneous but not 2 transitive, that means you can map any pair of points to any other pair, but only in one order. And in particular, it means that you can't swap 2 points over. So the group has odd order. So by the Feit-Thompson theorem, it's soluble. And using that, it follows that it's affine. If it's affine, you can throw minus the identity into the linear part and get a 2 transitive group. So the classification of the 2 homogeneous but not 2 transitive group follows from the classification of the 2 transitive groups. Well, it follows more easily because these are very special 2 transitive groups. So all these groups are known, and this was done independently by Bill Cantor and Berggren in 1969 or early 70s, sometime around there. And Cantor went on to find all the T homogeneous but not T transitive groups, so we have a complete answer to that question. Okay, so I'm going to spend the last bit of time telling you about another permutation group condition, which there's recently been some progress on. So we're defining permutation group properties by saying there's no non-trivial structure of some particular kind on omega. So I'm going to call a group X-free if it preserves no non-trivial X structure. So transitive is subset-free, primitive is essentially partition-free, basic is Cartesian structure-free, and I'm going to talk about several more of these tomorrow, but for now I want to describe a recent result that Sean Eberhard and I proved last year. And this also allows me to introduce an important tool for studying permutation groups, and also occurs in other parts of mathematics, and well, I'll say a little bit about it when we come to it. So, coherent configurations. So, I'll give you a definition in a moment, but Donald Higman defined these things. He was extending work of Schur and Wieland on permutation groups, but specifically I think what he was trying to do was decomposing permutation characters. If you have a group, if the group is doubly transitive, then in characteristic 0, the permutation character is the trivial character plus an irreducible. If it's not doubly transitive, that other bit is not irreducible anymore, so you would like to decompose it. And coherent configurations were a tool for doing such decompositions. At the same time, in the former Soviet Union, Weisweiler and Leman were working on graph isomorphism, and they introduced coherent configurations. So they called them cellular algebras. We can't call them cellular algebras anymore because that term's been hijacked for something completely different. But they call them cellular algebras for an attack on the graph isomorphism problem. And this is fed into the work of Babai on the graph isomorphism problem. So Babai's quasi-polynomial time algorithm for graph isomorphism uses these ideas on coherent configurations that go back to Weisweiler and Leman. And also R.C. Bose in the design of experiments in statistics. Though his were less general, as I'll come to in a moment. So they have very different roots. And last year, or was it the year before, there was a conference, the year before last, there was a conference in Pilsen, which, one of the things it did was to trace these different strands of the history and find out how they developed and how they got together and when people first realized that other people were doing much the same thing. For this, I'm going to take my set omega. We'll have binary relations on omega, and any binary relation can be represented by a 0-1 matrix. I put entry 1 if alpha and beta satisfy the relation, and 0 otherwise. So I can define this in terms of relations on omega, or I can define it in terms of 0-1 matrices, or I can mix the two things up. So a coherent configuration is a set of binary relations on omega such that 4 conditions hold. Firstly, these relations partition omega cross omega. Every pair satisfies exactly one of them. A subset of the relations partitions the diagonal. If you take the converse of a relation in C, that's also in C. In other words, if you take a relation, you turn all the ordered pairs around, that will be another relation in your set. And the final condition is much more easily expressed in terms of matrices. The linear span of the relation matrices is closed under matrix multiplication, which you can write down as a combinatorial condition on the relations, but it's much easier said in that form. And so in particular, this means that the relation matrices span an algebra, which is called the Bose-Mesner algebra of the configuration. Now, I've mentioned Bose's name before, Mesner. Mesner constructed the Higman-Sims graph more than 10 years before Higman and Sims. With his bare hands, he knew nothing about permutation group theory. He just constructed this graph, proved its uniqueness, didn't look at its automorphism group because that wasn't the sort of game he was playing. So, one of the forgotten heroes of sporadic simple group theory. So the relation matrices over C form span a semi-simple algebra, Bose-Mesner algebra. Now, if you take a permutation group, then you can look at its orbits on omega cross omega. They're relations, and it's easy to check that they satisfy all those conditions. And indeed, the Bose-Mesner algebra is precisely the centralizer algebra of the permutation group, the matrices that commute with all the permutations. And these are sometimes now called Schurian. If all the matrices are symmetric, then the configuration is an association scheme. And this was the class of things that Bose came up with, association schemes. Well, Bose was a statistician. Statisticians deal in real data. They deal with covariance matrices which are always symmetric, and so it was very natural just to stick to real symmetric matrices. So an association scheme is a coherent configuration in which all the relations are symmetric. Okay, so what are the trivial coherent configurations? Well, there's the partition into singletons, and there's the two-part partition where the relations are the identity and everything else. So inequality, equality and inequality, if you like to put it that way. So two. So that's the sort of one at the top, and the one at the bottom is where all the parts are singletons. So those are the trivial coherent configurations. So we can define a group to be CC free if it preserves no non-trivial coherent configuration. What are the CC free groups? Well, in a CC group, by the same argument we use for transitivity, in a CC free group we can map any ordered pair of distinct elements to any other ordered pair of distinct elements. So they're the two transitive groups. So CC free groups are precisely the two transitive groups. What about the AS free groups? What about the groups that preserve no non-trivial association scheme? Well, which are they? Certainly the two homogeneous groups are AS free, because now our relations have to be symmetric, so two homogeneous will be enough to make it AS free. There are others. Okay, so let's go through our hierarchy. If G is transitive but imprimitive, it preserves a partition. If you have a partition like this, you can make an association scheme where there's one part for the diagonal, one part for pairs in the same part of the partition, one part for pairs in different parts. This is what statisticians call a group divisible association scheme, but they use the word group in a different sense from the sense that we use it in. So an AS-free group has to be primitive, otherwise it would preserve something like that. If G is primitive but not basic, it preserves a Hamming association scheme. So remember that in a Cartesian structure you have this Hamming distance, so you can take the relations Hamming distance 0, Hamming distance 1, Hamming distance 2, and so on all the way up. That turns out to be an association scheme. So if the group is AS-free, it can't preserve one of those, it must be basic. And therefore, according to Nan Scott, it must be affine, diagonal, or almost simple. Well, an affine AS-free group must be two homogeneous, and the reason is as follows. You look at the Bose-Mesner algebra of the coherent configuration. So that's this is coming from a group now. Well, this is an affine group, so it's got this translation, this abelian translation group. And it's so that abelian translation group, so everything in the centralizer algebra of this group will be a linear combination of matrices in that abelian subgroup. Right? They all commute, so I can add one to its transpose and preserve the property of being a coherent configuration. So I can just symmetrize this coherent configuration and get an association scheme. If the association scheme I get is trivial, then the original coherent configuration must have been either trivial, well, the group must have been two homogeneous. So basically, affine AS-free groups must be two homogeneous. Yes, okay, so what diagonal groups? Well, if you have a two-factor diagonal group, remember that we could represent this as T cross T acting on T, where one factor acts on the left and the other factor acts on the right. And it's easy to see from that that it preserves an association scheme. You take the conjugacy classes, and for each conjugacy class you put it together with its inverse, that will symmetrize, and those are your relations basically. If X inverse Y lies in C union C inverse, that's one of the basic relations. That's an association scheme. So two-factor diagonal groups are not AS-free. Three-factor diagonal groups, I already said they preserve Latin square graphs. Latin square graphs are association schemes. Remember, there are the graph that you have the cells of the Latin square, you join two things if they're in the same row, same column, or have the same entry. So that's one relation, and the other relation is everything else, and then equality. That's an association scheme. So three-factor diagonal groups are not AS-free. What about more factors? Well, you can actually construct association schemes for D-factor diagonal groups for all D greater than or equal to 3. And this is what Sean and I were able to achieve last year. So there are association schemes preserved by all of the diagonal groups. So a transitive AS-free group is either too homogeneous or almost simple. Two homogeneous groups we know. What about almost simple? Well, there are some. PSL 3,3 acting on the cosets of the orthogonal group, degree 234. M12, degree 1320. J1, 3 actions of J1 are AS-free. J2, 1 action. That's all I know. Problem. Make some sense of these almost simple AS-free groups. You know, this scruffy list here is what's going on. Why are we just getting those? I haven't done a systematic search, but back in the days before the fall of communism, the people in the Soviet Union had done extensive computations on working out the, well, taking a simple group of order, I can't remember how far the orders went up, taking simple groups, looking at all their transitive actions, working out all their, their primitive actions, working out the coherent configuration, and working out all ways that you could glue relations together to make a coherent configuration. In particular, you can read off from their list when it's possible to glue relations together so that all the relations are symmetric and form a coherent configuration. Well, those are the groups that are not AS-free. The ones where you can't do that are the AS-free groups, and in their list, these are the only ones that come up. But I think now we have the technology that we could actually push this along quite a bit further, and so it would be nice to think that we can actually make some sense of this class of groups. So that's all I have to say. There are some references. Ashbacher's theorem. Here's the paper on association schemes for diagonal groups. There's Feinkanter and Schacker. There's the book by Prager and Schneider. And finally, this paper that I highly recommend to you, Sayre's paper on a theorem of Jourdain. Well, just in my closing moments, let me say, Andy Warhol said we should all have 15 minutes of fame. My 15 minutes of fame came when Queen Mary decided to give an honorary degree to Sayre. So he came over and he accepted the invitation to give a lecture beforehand. And the title of his lecture was On a Theorem of Jourdain. And he didn't say which theorem of Jourdain, because Jourdain has many theorems. It was the one about transitive groups containing a derangement. And it was the content of his beautiful lecture was essentially the content of this paper. And he said, Jourdain proved this theorem in 1871. It took 120 years for that to be quantified. It was quantified by I.A. Cohen and me. We proved that in a transitive group of degree n, at least a fraction 1 over n of the elements are derangements, and that's best possible. So anyway, thank you for your attention. That's it from me. Charlie Sims classified them up to degree 50, yes, yes.
Wouldn't he have done 34 before the classification was 50?
Yes, that is true, that is true.
I don't think he ever published it. But
no, he never published it. It was published up to 20,
yeah.
which wouldn't be enough.
Yeah.
So if someone hadn't known that Sims had done this, they might very well have sat down to say, can I do 34? And they probably would have hacked it out after quite a lot of effort, but yes, it would have been a bit of a job. But as I say, now we know that they're the exceptions, and the rule is that the only primitive groups are Sn and An. I can't see where the pointer is. I'm just going to leave that.